We hope you've been enjoying the Discovery Dialogues podcast, where we tell the stories of biomedical discovery the way they deserve to be told, not as dry timelines or textbook summaries, but as deeply human stories, filled with uncertainty, obsession, rivalries, accidents, setbacks, turning points, and moments that changed medicine forever. But behind every discovery is a person: scientists whose careers took unexpected turns, ideas that were dismissed, ignored, or met with skepticism, experiments that failed again and again before finally revealing something extraordinary. And sometimes scientists who did not even realize in that moment that they had just changed history. In our Deep Dive series, we bring you the full conversations with these remarkable people. Join us for Discovery Dialogues Deep Dives.
Today we're speaking with Dr. Jens Juul Holst, a physiologist at the University of Copenhagen whose work was central to understanding incretin hormones and who isolated and characterized GLP-1 from intestinal tissue, establishing its role as primary incretin in humans. Apart from being one of the co-discoverers of GLP-1, Dr. Holst has received some of the most prestigious honors in science, among them the Breakthrough Prize, the Tang Prize, the Canada Gairdner International Award, and the Banting Medal. And we are truly delighted that he joined us. Hello, thank you so much for joining us.
Very welcome.
Really, our goal with this podcast is one, to make science accessible, but also to make a general audience appreciate what goes into these breakthroughs at the level of the personal work that the scientists do and the years of struggles and minute steps and how much it takes to actually bring these things to therapies. So thank you so much for taking some time.
You're welcome.
I read about your journey. In the beginning, you started as a surgeon. And I read in the Lancet that it said that from the first day in the Department of Surgery, I was completely hooked and thought surgery was my future.
Absolutely correct.
So could you tell us a little more about that moment? What drew you so strongly to surgery in the beginning? And what made you ultimately pivot away towards physiology and towards hormones?
So I had done some training in anesthesiology already, and I had been working at one of the Copenhagen hospitals for a couple of years as a kind of substitute anesthesiologist. I had some special courses, so they allowed me to do that. So I was quite well acquainted with the whole atmosphere and what was going on and all that. And I was actually considering anesthesiology might be my field. And then I got my first position in surgery. And I realized that surgery was it. And I was quite good with my hands already. I was extremely lucky because they had some shortage of staff at the department. And I had a talent, so they kind of relaxed, and let me do it. So I was absolutely absorbed. But what happened was that our department became a university department. So the head of the department became a professor. He should have a kind of scientific assistant. And I was appointed as the assistant to the professor. So that was the beginning of an academic career. Of course, we were interested in science. This was, after all, a big Copenhagen hospital. So we were interested in also doing science. And I quickly became interested in the hypoglycemia that some of our patients developed after operations for peptic ulcer disease, which was the great thing in those days in the 1970s. Then I got together with a guy called Jens Rehfeldt, who was a similar age as me, but had already done a lot of work in the field of gastrointestinal hormones. And he was interested in gastrin. And we focused on incretin action, the regulation by GI hormones on insulin secretion, because my patients with hypoglycemia, they had it because of hyperinsulinemia, too high levels of insulin. So the theory came up very quickly that perhaps we were looking at an effect of insulin-releasing hormones from the gut. That became my kind of destiny in science. It was not because I was not interested in the surgery any longer, on the contrary, but it was very inspiring. We had a lot of great times. We created a laboratory together, this and I and a couple of other people, and we were doing research in the gastrointestinal hormones, and it was a lot of fun. So, eventually after some years, I had done more research with the hormones than I had done surgery. And then I was kind of caught in the research business because it was really off. It was interesting, but it was exciting. So eventually there was a position at the university after 7 years. I applied and got that position, and that became my destiny. I
Oh,
continued to do experimental surgery on pigs, and I really had a
right.
lot of fun with that. And we
Yeah.
created some really wild models with nerves regulating all sorts of organ function and things like that.
So, what was one of your wild models?
So I had models of the pancreas where I could stimulate the autonomic nervous system. So separately,
Oh,
the vagus system and the splanchnic innervation, the sympathetic nerves to
yeah.
pancreas. So I did that, really did a lot of efforts to study very carefully the effects of the autonomic nervous system on the pancreas, on its
Oh,
functions, both the exocrine, both the juice, and the
yeah.
hormone. I really did a lot of work in that field, and it was
Yeah,
fun because I
yeah.
had this model, the perfused pancreas, which was alive and could lie there and spit, produce juice. Pancreas would come out in large quantities. It was really fun.
So, in an earlier episode, when we go into the history of diabetes, we talked about the fabulous surgical skills of Oscar Minkowski and how he
Yeah,
removed the
a good old
Yeah.
pancreas
guy.
and
Yeah,
keep
yeah,
the
yeah.
dog alive, and that just led to this big discovery. And
Hmm.
you've done actually the opposite, where you keep the pancreas outside alive
Yeah.
and
Yeah,
leave.
yeah. But the fun thing is that I'm still doing this, not in pigs any longer, but we do it in mice and rats. And that's because I think it's one of the most reliable ways of getting to know what really goes on in the pancreas. Other experimental models have some limitations that make them not completely translatable, whereas this model should be directly translatable to real physics.
Right,
And that's why we
right.
love it so much.
It's worth noting that this same perfused pancreas model, developed in the 1970s, became the key tool that allowed Holst to test whether the GLP-1 from intestinal extracts was actually biologically active.
Let me tell you about one of the things. So I'm trying
Yeah.
to find out why people with type 1 diabetes cannot produce glucagon when they get hypoglycemia. We think that there is a mechanism inside the pancreas that goes wrong, and we think it has to do with one of the hormones, the other hormones from the pancreas called somatostatin. We're trying to find out if we can understand exactly what goes on. We have models of type 1 diabetes. So that's one of the main things we're
Oh
doing.
my gosh. Okay, I have to tell you one thing we were fascinated by. We did an episode on cone snails that
Yeah, yeah,
hunt fish
yeah,
with
yeah.
barbs filled with insulin, right?
Yes,
To
yes,
put
yes,
them
yes,
in
yes. Yeah.
hypoglycemic shock. But what amazed us is that the poison sac and the poison in the barbs doesn't just have insulin, it has somatostatin to
Exactly.
block their
Exactly.
glucagon response
Exactly.
so they
Yeah,
can't
yeah.
recover.
That's
Isn't
Yeah,
that
yeah.
amazing.
crazy?
It's an absolutely fascinating story. Yeah, I know it very
Yeah.
well. I've contributed to some of the work there.
How were you involved?
We studied some of the somatostatins from the cone snails and their effects
Oh,
on the pancreas, of course,
oh
Wow.
my gosh.
and all that. Yeah, yeah.
We were thinking about how the work that was happening on the East Coast of the US and then your work, how eventually the studies kind of converged to give a whole picture, even though you took different approaches. But I was thinking that when you were first doing this, you wouldn't know immediately what other people were doing like we do now. It
No,
could be a total surprise.
yeah. Eventually, I met with Joel Hebner and
Uh
also with Svetlana Moisov at meetings. And we
huh.
were talking together. So we knew about each other. We knew about
Uh,
the existence of each other.
uh,
Of course, I knew about Joel's work with the fish.
The convergence of the Copenhagen and Boston groups from opposite directions, classical peptide isolation versus molecular biology, is one of the defining features of the GLP-1 story.
This was conducted by a researcher called Pauline K. Lund, postdoc, and she came from Copenhagen. She had been working with
oh,
us for a couple of years, and she was extremely good at drinking beer. She was really a great girl, really fantastic. So we loved her very much. And so she had got this position with Joel and was the first author of the paper about the pro-glucagon molecule
yeah,
from
yeah,
the
yeah.
fingerfish. She then
Yeah.
moved to Chapel Hill to become professor of physiology there. I mean, that was why we were following very, very closely what was going
Oh,
on. Also, he was introducing Joel molecular biology into this. And so we followed different paths with us. We went the classical way of isolating the peptides from the body, the natural peptides. So no speculation. We simply went for the molecule itself, for the peptide.
yes.
pulled it out of the extracts and purified it and put it on my pancreas again. And we could see that it did all that it was supposed to do.
To get enough, how much intestine did you have to start with to purify?
Already in those days, the methods had improved quite a lot. So we did study, let's say, gram sizes, 10 to 20, 40 grams. That would be sufficient. It was not terrible, but there was a certain smell in the laboratory those days when we were boiling gut extracts, and things like that.
This is where things begin to shift. The moment the two groups working independently discovered that the full-length molecule they'd been studying was not the active form.
So we knew about what was going on in Boston very well, indeed. And we were wondering which approach would be the fastest. And what happened was that Graham Bell, who was from Chicago and working with the Lilly company, actually also using molecular biology, found the structure of the hamster proglucagon. Mm-hmm. And fortunately, half of that molecule was the same that we had been able to pull out of the gut. The molecule that is called glycentin, which has glucagon in the middle. But he was also the one who found this tail of the proglucagon molecule where there was two glucagon-like stretches in. And they were much more glucagon-like than the fish glucagon-related peptides. So Svetlana looked at this structure, and so did we. And we synthesized it, and so did Svetlana. And I put it on my pancreas, and it didn't work. It didn't work at all. And that's why we, realized that we had to pull out the real peptide ourselves from the gut, and that's what we did, and it worked. So Svetlana looked at it and said, if we take away the first 6 amino acids from this predicted structure, maybe it would be more glucagon-like. And she synthesized that and put it on, had Gordon Wehr from Howard, put it on this, and then it stimulated the insulin secretion. So, we got to the same result in two completely different ways, but the result was the same nevertheless. And also our results came out almost simultaneously in February 1987.
And can you, just for our audience, what's the simplest way to think about the incretin effect?
So we have hormones that are secreted in the gut. And what they do is to stimulate insulin secretion, and they're secreted when you eat. So they're being stimulated by food intake, nutrients. And it turns out that to be able to secrete sufficient amounts of insulin, we need these hormones. They need to stimulate insulin secretion much more than glucose alone or amino acids alone. It's about 3-4 times more. It's really, really important. And if you don't have them, then you get glucose intolerance, then you get diabetes. So you need them. So they are very, very efficacious in terms of regulating blood glucose in this way. So it's an absolute necessity to have the incretin hormones when you eat, because otherwise you cannot produce sufficient amounts of insulin.
I read the other part of the incretin effect, Dr. Holst, is the finding that the effect on insulin of oral versus intravenous glucose was very different. You've done a lot of very important work on that. So could you just elaborate a little bit for our audience?
Yes. So the way you do it technically when you study this in people is that on one day you give them some glucose to drink, and then you take blood samples over the next couple of hours and measure insulin, right? Then on the second day, you give them an IV intravenous infusion into the blood vessels of glucose. With a bit of training, you can organize it so that, or you can adjust the infusion rate so that the glucose concentration in blood becomes exactly the same as it was on the day before. So now you have completely the same glucose concentrations, right? And then again, you measure insulin, and then you can see that on the day where you infuse the glucose, the insulin response will be small. On the day when you were drinking it, it is 3-4 times higher. That's how you do it. That's how you quantitate it. You measure the incretin effect.
And are you still having to do this by ELISA, or what's the modern way?
The measurements of insulin is by ELISA. Yes, that's right. The actual technique is that you have a student who takes blood samples every 5 minutes to make sure that the glucose is the correct one, and adjust the infusion rate. So there's a lot of work to that.
Yeah.
The continuous monitor here is the student.
The continuous monitor. That's great.
Yeah.
Ani, you wanted to ask something about craving and reward?
Yeah.
Beyond. Ani's next question about satiety and addiction touches on what's become a most surprising and consequential frontier in GLP-1 science, the brain.
So, one of the really cool things that I find is that the effect that you have published and others on satiety. And what I find fascinating is that it's not just food cravings, but many other forms of addiction. So, we would love to hear your thoughts on GLP-1 and satiety for food cravings and then satiety in general.
Yeah. Yeah. So what happened was, of course, that we were interested in the regulation of food intake because it was the kind of thing you did when you were interested in gut hormones, looking at appetite regulation, because there had to be some signal from the gut to the brain saying that now there's enough food here. And there was already one hormone that was under suspicion, the hormone called cholecystokinin, CCK, demonstrated to inhibit food intake in rats in 73, actually. So on the agenda all the time that we should do that. So eventually we started looking at it and we found that sure enough, it did inhibit food intake, the GLP-1 molecule, and in a physiological way so that we could consider it a physiological regulator of food intake. I mean, there are many ways you can make people lose their appetite by giving them a bit of nausea or, something like that. But in this case, there was no nausea. So it's a real effect. And we know that today, of course. But around 2000 and 2010 and so there were several scientists that were interested in the reward mechanism and did a lot of studies on the neural pathways. And eventually, the two fields merged, and it was realized that GLP-1 would activate some of these reward mechanisms in the brain. So this was quite well worked out in rodents and by these neurobiologists. But and also, eventually it also was possible to demonstrate that infusions of GLP-1 in people would hit those nuclei in the brain. And some of the imaging studies also supported that. So more and more, we think that it is true that there is this reward. And actually, if you look at people-reported outcomes when you ask people how they feel about this, they all come up with some, remarks that, yeah, now I lost the interest in that, and I lost the interest in that. And some of them, lament very much because they all of a sudden lost the interest in red wine and things like that. And so bringing it all together is that a considerable part of the food intake limiting part is that you remove this reward mechanism from people. And that is what has now been studied and realized in cases of abuse and alcoholism. And we've just submitted a major paper about this, and it works very, very well. Semaglutide treatment for alcoholism.
Oh, wow.
So that is really very, very promising. But of course, it's also a bit of a difficulty because it does take away some of the pleasures of life. So if you are a person, who has become obese because you love food, and this eating process is the biggest thing in life, and you take it away, what is left then? It's terrible. It's going to be miserable. So it's a kind of two-edged sword, this thing, right?
Yes.
This tension between therapeutic efficacy and quality of life is not peripheral to the GLP-1 story. It's central to how these drugs will or won't work at the population level.
I usually bring up this topic when people, think that I'm suggesting that half the globe should be on a GLP-1. And I say, this is not going to happen because people will not be happy about it.
Wonderful. So, one of the things, even beyond addictions, now there are thoughts about could these drugs help with longevity in general? Yeah. And we're so struck that metformin, that works by totally different mechanisms to control blood sugar, and SGLT2 inhibitors that work by yet a different mechanism. And yet they're all being thought of as potentially beneficial for longevity. So do you think that sugar control is central?
Not really. But on the other hand, chronic hypoglycemia, too high glucose over a long time, is clearly not beneficial for anything, and the glycated end products and all that. So you will have damage on your proteins if you have a high. So if you can do something about that, and that's what we can do with the GLP-1s, of course, then it is beneficial. But it was actually striking. It was already at the registration studies for exenatide, the Byetta compound that was introduced as the first, actually, in 2005 by Emily Pharmaceuticals.
Yeah.
They did a tox study in mice and rats. They dosed them for a lifetime with high doses of exenatide. And it turned out that the higher the doses were, the longer they lived. Quite significant.
What makes this important is what that lifetime dosing study implied, not just about exenatide, but about the relationship between caloric restriction, body weight, and longevity that runs through all of these drug classes.
It's really a large part of their lifespan that was expanded with the therapy. The most reasonable explanation for this is the weight effect. It is known that if you put rodents on a diet, if you reduce their calorie excess, as you can do experimentally, of course, they will live longer. So this is a well-known biological phenomenon. Yeah. But it was very striking that you could reproduce this phenomenon with exenatide. Very much. Now, exenatide is not a fantastic drug any longer. I mean, it has pharmacokinetic problems and all that. But there's no doubt that if you can maintain a lower body weight, then you will also be able to live longer. I think this is well supported throughout. If there are also other mechanisms, yes, I can think of several, because I mean, we have to die of something, and most people die from cardiovascular disease. And if you prevent that from happening, it seems that you can do that by a couple of mechanisms that the GLP-1s are involved in. Then, of course, you have a good ground for believing that this will help in longevity. And let me point out another thing that I think is really interesting. That is the results of bariatric surgery.
Yeah.
I looked at recently, and there was a major meta-analysis with almost 200,000 individuals that were looked at. It was found that their life expectancy, if they had diabetes at the time of operation, was expanded by 9 years. So they had a 9 years longer lifetime. If they did not have diabetes, the life expectancy was 5 years longer. And that's, of course, because you...
they were going to live longer anyway.
Exactly.
So do you think there might be a different... I know with bariatric surgery, you can either just close off part of the stomach, or you can remove some of the small intestine as well. Do you think the effects are different depending on which surgery? I ask because then you're talking about absorption besides how much food can be ingested.
So we've really been working a lot with bariatric surgery, trying to understand the mechanism here. And I must admit that I know most about the one which is called gastrectomy, the Roux-en-Y gastrectomy. But we've also looked in detail at the sleeve gastrectomies that you talk about. But they're not completely identical. One of the mechanisms behind the sleeve gastrectomy appears to be another hormone, which is called ghrelin in the stomach. And if you take out the stomach, then you don't produce ghrelin any longer. And ghrelin stimulates appetite and food intake. So here's one mechanism that may be important here. But for the other one, for the gastric bypass, there's no doubt that there is an up to 30-fold increase in the secretion of GLP-1 and another hormone, which is called PYY. We've actually demonstrated in some experiments in people that this is the explanation for how they lose their appetite and eat less. So I think it's reasonable to compare the therapy with these hormones and the results of surgery, because they really use the same mechanisms. I can't prove that the GLP-1s will give you 9 more years. I can think that they will give you something.
In the broader context, the comparison between drug and surgery is not just mechanistic. It points toward what may be the defining challenge of the GLP-1 era. Not efficacy, but durability, cost, and access.
We see that you've written a book. Yeah. That's not quite released yet. Is that correct?
So you can buy a Danish version, but actually it will come out very soon.
That's wonderful. We look forward to that.
Are
Yeah.
there any anecdotes that you would like to share with our audience?
The most important is that it's been a lot of fun. I mean, I've really enjoyed working with this for the last many, many years.
Mm.
And in general, it has been really a lot of fun, I would say. Yeah, because in a position like ours, you take in a number of students and they work with you and then they move on. And so there's a constant traffic of young people in your laboratory. And it's absolutely amazing to be able to
I
work that way.
A philosophical issue that I've been very pleased about with the GLP-1 drugs coming on board is there have also been major efforts by drug companies to block absorption. And coming from a country that's so wealthy and we already consume more than our share of the world's resources, to me, morally, I had a problem with us now all just eat with impunity all day long with no consequences and not even absorb the calories when people starve elsewhere in the world.
Okay.
It's a relief to me. Let's block satiety
Yeah.
instead.
Yes, I agree a lot because I've been thinking a lot of what is the most rational way of solving this problem? How do you do it
Exactly.
best? And some people think that you should expand the energy expenditure, and that has turned out to be dangerous in almost every case. Because what happens is that this puts a challenge on the circulatory system, on the heart, because
Oh,
you
yeah,
must get
yeah,
rid of the heat, of course. And
yeah,
eventually you will have a problem. I mean, some people will have a problem. They cannot
yeah, yeah.
do this, and that's dangerous, of course. That's why I'm almost all attempts to make weight loss by increasing energy expenditure, except for exercise, of course, which is good. They have failed. So it's a much more sensible and reasonable way to inhibit appetite. I think it's such a logical and wonderful approach.
Well, now that you mention that energy expenditure, even the efforts to turn white fat to brown fat,
Yeah, yeah,
it
yeah.
still
No.
means we're going to just continue to use all the resources and then just blow them away
Yes,
instead
yes.
of go to anybody's benefit.
Yeah, yeah, no,
Um,
I completely agree. I completely agree. But have you seen the last data regarding the weight, the body weight in America, in the United States? It's
oh,
falling for the first time.
I know because
And
very recently, life expectancy in the US was going down
yeah,
because
I
of
know.
obesity.
Yes, yes.
And sadly, the life expectancy of children born
Yeah, yeah,
was going to be lower
yeah,
because of
yeah,
obesity in children.
yeah, yeah. Fortunately, we are engaged in a project here in Denmark where we are looking at adolescents with severe obesity and where we're treating them with Wegovy, and it works very, very well.
Oh,
These are children that or young people that have been given up by the health authority, the doctors, because they were completely impossible. They were completely resistant to whatever you did. Wegovy, and it works. It's very important to think, because this is a surprise that we all of a sudden have a drug that can regulate body weight for everybody, really. But so how do we deal with this? And that's where I think that those that are at risk for
yeah,
complication of their obesity, they are the ones who should have it. And I think
yeah,
this is something that we need to discuss in the various countries and the various governments and political bodies. How do we make sure that this can be done in a reasonable way and distribute this wonderful thing? How to ensure that there will be an access
yes.
to people that need it. It's about a quarter of the adult population benefit from this, have a longer life and a life more free of complications. So I
Yeah.
think that's
And
very
even if
important.
they don't have the funds, if you look at the long-term cost that missed work and the complications and ultimately diabetes would have on the
Exactly.
economy,
Yes, yes, yes.
but then there's the issue of do they need to take it for life?
No, I think there is a lot that can be done. So while you're on the therapy, 1 year or 1.5 years, that's when the actual weight loss levels out and you get to the target. That's an extremely important period in your life where you can adjust your eating habits, and it's possible because you are relieved of the murmur of, the noise of food, control for the first time in many years of what you eat. So you can do it. You can change your diet. And the other thing is that you should also use that 1.5 years, change your exercise habits. And again, you can do it because you lose weight, and joint pain will disappear. And it doesn't really take a lot. The WHO recommendation of 30 minutes walk per day, that's all it takes. Then you may
Yeah,
be able to maintain the weight loss
right.
automatically. And if you don't, then there are still other options. For instance, smaller doses.
I was going to ask you, you hear so much about microdosing.
Exactly.
You
And
think
so
it's real?
yeah, absolutely. So one experience from that is that you may be able to dial down the dose after many ways that are not sufficiently explored yet. And I even saw some people suggesting that you could use metformin to maintain the weight loss, which is really, really accessible, right? Yes.
Yeah.
So, I mean, there are many ways that are not sufficiently explored yet. No, I don't think you have to be on it all your life.
You know, it's amazing to think what the next 10 years will teach us about these powerful drugs. This is such a joy to us, but we're going to let you go. Thank you.
You're welcome.
Thank you for listening to this Discovery Dialogues Deep Dive. Stay tuned for more conversations with scientists whose work has shaped how we understand and treat disease.